Problem 6. How much energy is carried by a photon of blue light with wavelength 430 nanometers? And B, does a photon of yellow light carry more or less energy than a photon of blue light? Try this calculation in part A and this explanation in part B on your own first, and then we'll go over the answers in the next couple of slides. All right, so here's the solution here to part A of problem 6. How much energy is carried by a photon of blue light, 430 nanometers? We're given the wavelength of that light, 430 nanometers. First thing I do is convert that into meters. 4.3 times 10 to the minus 7 meters. And then using this equation that we have for the relationship between energy and wavelength, we solve for energy. So we know that energy is equal to Planck's constant times speed of light, c, divided by the wavelength, lambda. Substitute values. So here's Planck's constant, 6.626 times 10 to the minus 34 joule seconds, times the speed of light, 3.00 times 10 to the 8th meters per second, divided by that given wavelength, 4.3 times 10 to the minus 7 meters. And just to show a little unit cancellation here, meters and meters, seconds and seconds, and we're left with 4.62 times 10 to the minus 19 joules. All right, in the previous problem, we found out how much energy was carried in blue light, right? A photon of blue light. And now we're being asked to compare. Does a photon of yellow light carry more energy or less energy than that photon of blue light that we just calculated? And the answer is a photon of yellow light carries less energy. Less energy. Now we need to explain, right? In an AP problem, we can't just answer the question. We need to answer the question and provide a justification. So the wavelength of yellow light is between 570 nanometers and 590 nanometers. So yellow light has a longer wavelength. If you think of your electromagnetic spectrum, right? Your visible light spectrum, in the middle of your electromagnetic spectrum, you have Roy G. Biv, right? Okay, now this way, below red, you have infrared. I'm thinking ahead to the next one. Below red, you have infrared. That's what infra means. It means below. So below red, and above violet, you have ultraviolet. And you can think of even below infrared where you have radio waves and microwaves, and how above ultraviolet you have gamma, right? And so you can think of those things, but think about what's happening to the wavelength as you start over here, right? Your wavelengths are long, and then they get a lot closer together. Okay, so as you go towards the left on your electromagnetic spectrum, the wavelengths are longer. As you go to the right on the electromagnetic spectrum, those wavelengths are shorter, and the frequency of them, their repetition, increases and increases and increases. And so does energy, right? As we go this way, energy increases. Okay, so yellow light has a longer wavelength than blue light, 570 to 590 nanometers. That means the wavelength is greater than that of blue light. Given that same equation that we considered on the previous slide, wavelength is inversely proportional to the energy. So the greater the wavelength, the longer the wavelength, the lower the energy. Since the wavelength of yellow light is greater than that of blue light, photons of yellow light carry less energy.